Right, I'm going to go over an AQA past paper. It's for triple science, single physics. You can tell because it's 1 hour and 45 minutes. It's a higher tier, paper 1, and it's from Wednesday the 23rd of May 2018. 100 marks in total. Question 1. Figure 1 shows a student walking on a carpet. The student becomes negatively charged because of the friction between his socks and the carpet. Explain why the friction causes the student to become charged. The answer is always the same. Electrons are transferred from the carpet to the student. You'll notice that every time I'm putting a bullet point, I'm expecting a mark for the statement that I've said. So 2 marks, 2 bullet points. Part 2. The student's head is represented by the sphere in figure 2. The student is negatively charged. The arrow shows part of the electric field around the student's head. Draw 3 more arrows on figure 2 to complete the electric field pattern. So I'm just saying here, remember that electric fields are circular. They act in all directions. This is coming in, so we'll make sure that these are all coming in as well. So they are the 3 lines that you need to draw. Part 3. The negatively charged student touches a metal tap and receives an electric shock. Explain why. Again, the answer is always the same. So the student's charged and the tap is not charged. So there is a difference in potential. So that's what we call potential difference. The student's got some voltage built up on them and the tap hasn't. And this difference will cause charges, in this case electrons, to transfer or flow from the student to the tap to try to balance out the charges. So there's no difference in the voltage that's on the tap compared to the voltage that's on the person. That's how it happens. And the charge will go to the earth, and that's why they get an electric shock. As the electrons, as the charge is leaving the person's body, that's when they'll get a shock. Part 4. Some carpets have thin copper wires running through them. The student is less likely to receive an electric shock after walking on this type of carpet. Can you suggest why? For 2 marks. Right, well, I've put a lot more than just 2 marks here for you. Remember, copper is a good conductor, so electrons, or the charge, does not build up, it'll flow away, and so the potential difference, the voltage, does not build up, and so they are less likely to receive an electric shock. Pause the video if I'm going too fast. Question 2. A teacher used a Geiger-Müller tube and counter to measure the number of counts in 60 seconds for a radioactive rock. The counter recorded 819 counts in 60 seconds. The background radiation count rate was 0.3 counts per second, so that means the background before the rock was put in it. Calculate the count rate for the rock. So the count rate is how many counts there are per second. That's what rate means, how often something happens per second. So 819 counts or clicks in 60 seconds, so that means 13.65 clicks per second. Now we need to correct that count rate. Take the count rate of the rock and the background and take the background count rate away from it, and that will give us the count rate for the rock. Part 2. A householder is worried about the radiation emitted by the granite worktop in his kitchen. 1 kilogram of granite has an activity of 1,250 becquerels. That's how many clicks there are per second. The kitchen worktop has a mass of 180 kilograms. Calculate the activity of the kitchen worktop in becquerels. So 1 kilogram of granite has that many becquerels. So if we've got 180 kilograms of granite, we need to take that value and multiply it by 180. And it comes out as 225,000 becquerels. Part 3. The average total radiation dose per year in the UK is 2 millisieverts. Table 1 shows the effects of radiation dose on the human body. So 10,000 millisieverts is immediate illness or death within a few weeks. 1,000 is radiation sickness unlikely to cause death. And 100 is the lowest dose with evidence of causing cancer. The average radiation dose from the granite worktop is that many millisieverts per day. Explain why the householder should not be concerned about his yearly radiation dose from the granite worktop, and 1 year is 365 days. So the yearly radiation dose will be the daily radiation dose multiplied by 365 days. So that was the daily dose, and multiply that by how many days there are in a year. So that is the number of millisieverts per year that the person will receive. Now, why is that nothing to be concerned about? Well, the dose is much smaller than the lowest dose with evidence of causing cancer. Now, you'll notice that I've used the exact same words that they used, and that's a good exam tip. Part 4. Bananas are a source of background radiation. Some people think that the unit of radiation dose should be changed from sieverts to banana equivalent dose. I've got a nice video on background radiation. Click the link if you want to see it. Suggest one reason why the banana equivalent dose may help the public be more aware of radiation risks. Well, people would be able to make more sense of the radiation data and compare radiation risks more easily. So if you saw a certain dose, you could say, oh, that's the equivalent of the dose from 4 bananas. So you'll realise it's nothing to worry about. Question 3. A student investigated how the resistance of a piece of nichrome wire varies with length. Figure 3 shows part of the circuit that the student used. Complete figure 3 by adding an ammeter and a voltmeter. Use the correct circuit symbols. So an ammeter is just a circle with an A. It goes in series. I've got a nice video to do with ammeters. And a voltmeter needs to be connected in parallel to the test wire. And it's just a circle with a V in. I've got a nice video to do with all the circuit diagrams, the circuit symbols, if you don't know what they are. Part 2. Describe how the student would obtain the data needed for the investigation. Your answer should include a risk assessment for one hazard or in the investigation. So remember, they are trying to work out what the resistance is when the length changes. So a risk assessment, whenever you're using electricity, a high current could cause heating of the wire, which could cause a burn. How do we minimize that risk? Well, if we increase the resistance of the variable resistor, that'll decrease the current. So there's the variable resistor there. So if we make that big, then the resistance of the full circuit will be bigger, which will make the current of the circuit smaller. And that'll stop the wire from heating up and stop you from burning yourself. Now, how to perform the task. You need to measure the length of the wire, measure the voltage, measure the current, use resistance equals voltage divided by current to calculate the resistance, and then repeat the above steps and calculate an average. Then we want to repeat all of the above steps using 6 different lengths. Make sure that you've got an appropriate range, so perhaps going from a length of 0 up to 60 centimeters, and get some nice intervals. So the interval is how far apart each reading is. So make the reading 10 centimeters apart. So in other words, 0 centimeters then 10 centimetres, 20, 30, 40, 50, 60. And then plot a graph of resistance against length to be able to spot a pattern. So resistance up the side, length along the bottom there. And they'll sometimes ask you if you know what range means and what interval means, so pay attention to that as well. Part 3. Why would switching off the circuit between readings have improved the accuracy of the student's investigation? Well, it's basically the temperature of the wire would not change. Remember, if you change the temperature of the wire, it's going to change the resistance of the wire, and that'll affect your results. Part 4. The student used crocodile clips to make connections to the wire. They could have used a piece of equipment called a jockey. Figure 4 shows a crocodile clip and a jockey in contact with the wire. So that's what the crocodile clip looks like. That's what the jockey looks like. How would using the jockey have affected the accuracy and resolution of the student's results compared to using the crocodile clips? So they're making sure you know what accuracy and resolution means. What I want to draw your attention to is that this jockey has got a very sharp tip which will increase the accuracy and the resolution. I've explained what that means here. So tick 2 boxes. So the accuracy of the student's results will be higher. Yes. Why? Well, a measurement is considered to be accurate if it is judged to be close to the true value. So with that sharp tip, whatever length this is, that sharp tip is actually going to be very close to what the length is. Okay, so to its true value. So if it's 540, then it'll actually be 540. It won't actually be 541. Look at how wide that is. That's probably spanning across 3 millimeters. That sharp tip there is just spanning 1 millimeter. And that takes us into resolution as well. The resolution of the length measurement would also be higher. Why is that? What's resolution? Well, resolution is the smallest detectable change. So with that very sharp tip, you'll easily be able to detect what millimeter you are actually on. Now, you'll have heard of resolution in the real life. If you've got a 1080p, that's got higher resolution than a 720p TV. And that's because 1080p's got more pixels, so smaller details can be detected. This video is in 1080p. If I didn't do it in 1080p, it wouldn't be as sharp. Now, if you've got a 4K television, that means you've got even more pixels. If you're watching a football match on 4K telly, you can actually see the blades of grass. You can see where one blade of grass finishes and the other blade of grass starts. So that's a high resolution. It allows you to have a very small detectable change. I hope that helps. Question 4. Figure 5 shows a cyclist riding along a straight, level road at a constant speed. Complete the sentences. As the cyclist rides along the road, the chemical energy store in the cyclist's body decreases. So his chemical energy is from his food. The speed of the cyclist is constant when the work done by the cyclist is equal to the work done against air resistance. Figure 6 shows how the speed changes as the power output of the cyclist changes. So power output in watts along the bottom, and there's the speed going up the side. Write down the equation that links power, time and work done. So it's just power equals work done over time. I've got a video with all of the equations on. Click the link at the top. Calculate the work done by the cyclist when the power output is 200 watts for 1,800 seconds. So work done, let's rearrange that. It's power times by time. There's the power, there's the time. You just need to multiply those together. And the answer comes out as 360,000 joules. Make sure your time's in seconds, make sure your power's in watts. Part 4. Calculate the percentage increase in speed of the Cyclist when the power output changes from 200 watts to 300 watts. It's quite a big question just for 2 marks. So we need to use the graph. So if we look at the power of 200 watts, that is a speed of 9.5 meters per second. And at 300 watts, that will be a speed of 11 meters per second. So the speed at 200 watts was 9.5, the speed at 300 watts was 11. So the increase in speed is 1.5 meters per second when they go from a power of 200 to 300. Now, how much has that increased? Well, the percentage increase of anything is take the difference, so how much something's changed, and divide it by the original size of that thing, and then multiply it by 100 to get it into a percentage. So the difference in speed is 1.5 meters per second. The original speed at 200 watts was 9.5 meters per second. So multiply that then by 100 and it comes out as 15.789 or 15.8% rounded up. Part 5. The maximum speed this cyclist can travel on a level road is 14 meters per second. How does cycling uphill affect the maximum speed of the cyclist? Explain your answer. Well, if you've got your maximum speed on a level road, that must mean that you're using your maximum power. So if you suddenly start going up a hill, you're going to slow down. So your maximum speed's going to be less, and that is because work needs to be done against gravity if you're going uphill. If you've ever rode a bike in real life, you'll know that. And the reason for that, for your 3rd mark, is that the cyclist was already given their maximum power, so there's no extra power available when they're going up the hill in order to maintain their original speed. Question 5. Complete the sentence. Choose answers from the box. The current through an ohmic conductor is directly proportional to the potential difference, or the voltage, across the component, provided that the temperature remains constant. Part 2. Figure 7 shows a current potential difference graph for a filament lamp. Explain how the resistance of the filament lamp changes as the potential difference across it increases. So I've answered this in a number of different ways. It's worth 3 marks. The basic answer is, as the potential difference increases, the current increases. We can see that from the graph. Potential difference is going up, the current's going up. And if the current increases, that'll cause the filament bulb to get hot. And if it gets hot, that'll cause the resistance to increase. So that'll get you your 3 marks. If you're wondering why does the resistance increase as it gets hot, well, you'll end up getting more collisions between the lattice, so that's the ions that make up the metal, and the electrons that's trying to move through the metal at higher temperature. We're moving into A-level stuff there. At higher temperature, the atoms or ions in the wire has got more energy, and so they move more, and the electrons get bumped into more than. Now, other ways that you can analyse it, remember resistance is the voltage over the current. 1 over the gradient will give us the resistance. So in other words, as the gradient gets flatter, the resistance is going to get bigger. So we can see here the gradient at first is very big, which means the resistance must be very small. And here you can see the gradient is getting flatter and flatter, which means that the resistance must be getting bigger and bigger. Because remember, they're opposites. If one thing gets smaller, the other thing gets bigger. It's an inversely proportional relationship between the resistance and the gradient. Part 3. Many householders are replacing their filament lamps with LED lamps, which are more energy efficient. What does more energy efficient mean? Now, people struggle with this question a lot, and it's really easy if you just consider answering it by using the efficiency equation. So efficiency equals the useful energy out divided by the total energy in. So if we want to increase the efficiency, making it bigger, all we need to do is make more useful energy come out for the same amount of energy that you put in. And that's what I've wrote there. A light-dependent resistor, LDR, is used to turn on an outside lamp when it gets dark. Part of the circuit is shown in figure 8. The light intensity decreases. Right, well, if you know anything about the LDRs, you should know that the resistance of the LDR will increase when it gets dark. What happens to the potential difference across the LDR and the current in the LDR? Now, the potential difference across here, as it gets dark, will increase. And that's because the resistance of the LDR is increasing. So you must know the relationship. If you've got a bigger resistance, it's going to need a bigger voltage. It'll take up proportionally more voltage. And what's going to happen to the current? Well, the current through the LDR will decrease. And that is because the total resistance of the circuit has increased. If it's getting dark and that resistance is getting bigger, basically the current through the full circuit will get smaller because the resistance of the total circuit has got bigger. More resistance means less current, remember. What is the resistance of the LDR when the potential difference across it is 4 volts? Right, well, this is all to do with the ratio of the voltages being equal to the ratio of the resistances. Or in simple terms, the voltage is shared in proportion to the resistance. What on earth does that mean? Right, well, it's told you that the voltage on this LDR is 4 volts. Now, I've got 12 volts in the entire circuit. So if this is 4 volts, then across here must be 12 volts take away 4 volts, which is 8 volts. Now you can see that this has got twice as much voltage as this. So that means that this must have twice as much resistance as this. It's as simple as that. So if that's 2000, this must be half of 2000, which is 1000. And that's what I've wrote there. Now, if you want to know the mathematics behind it, that's the ratio of the voltages. So I'll put the voltage of the LDR on the top and the voltage of the 2000 ohm resistor on the bottom. And that's going to equal the ratio of the resistances. So put the resistance of the LDR on the top, just like that was on the top before the LDR. And now the resistance of the 2000 ohms on the bottom. I could have flipped that side, in which case I would just flip that side. So don't worry about that. Now, if we put the voltage of the LDR in and divide it by the voltage on the 2000 ohm resistor, that's going to equal the resistance of the LDR divided by the resistance of the 2000 ohm resistor, which is obviously 2000. Rearrange that, so put the 2000 over on that side there. So the resistance of the LDR is 4 over 8 multiplied by 2000, which, as I said, is 1000. So the mathematics can sometimes make it seem complicated. This is what you're wanting to pay attention to. And I've wrote it again over here in green. Remember, there's always more than one way of explaining something. So a simple answer again is that the voltage on the LDR is half of the voltage on the 2000 ohm resistor. So that means that the resistance of the LDR must also be half. So the resistance of the LDR is only 1000 compared to this, which was 2000. And that's what you call potential dividers. They can be tricky, and they are involved in A-level physics as well. Part 6. Calculate the current through the LDR. when the resistance of the LDR is 5000 ohms. Give your answer to two significant figures. So if we take Ohm's law and rearrange it so that I, the current, is going to be the total voltage divided by the total resistance. So the total voltage is 12 volts and the total resistance will be 2000 ohms plus 5000 ohms. Remember, they've told us that the resistance of the LDR is 5000 now. So that's a total of 7000. So 12 divided by 7000 comes out as that. And they want it to two significant figures. So that just means the first figures that are not zero. So that's not zero. So that's where the significant figures gets triggered, the 1. And we want one more figure after that, then 7. Since that's a 1, that stays as 7. It's worth looking into significant figures if you don't know how to use them. Question 6. Smoke alarms contain an alpha radiation source and a radiation detector. Figure 9 shows part of the inside of a smoke alarm. The smoke alarm stays off while alpha radiation reaches the detector. Why does the alarm switch on when smoke particles enter the plastic casing? So what they're saying is that this alpha radiation source, as long as it's getting across into the detector, then the alarm will not go off. But as soon as the alpha cannot get across, then the alarm will sound. And you can see here, the smoke particles are basically absorbing the alpha and stopping the alpha from getting across. So the smoke particles absorb the alpha radiation and stop it reaching the detector. 1 mark. Part 2. Why is it safe to use a source of alpha radiation in a house? Well, remember, alpha can only travel a few centimetres in air, so it's easy to stay away from it. And if you are within a few centimetres of it, don't worry, alpha can't penetrate the skin. Plus it's in a plastic casing, so the chances are it won't even get out of that plastic casing. And if the plastic casing is 1 or 2 centimetres, then it definitely won't get out. Part 3. The smoke alarm would not work with a radiation source that emits beta or gamma radiation. Explain why. So beta and gamma can penetrate smoke and will still reach the detector even when there's smoke there. So no change in the count rate will be detected by the detector whether the smoke was there or not. I've got a nice video all to do with the penetration powers and the ionization powers and what exactly are the 3 types of radiation, alpha, beta, gamma. Check it out, I'll put the link at the top. Part 4. Figure 10 shows how the count rate detected from the radiation source in the smoke alarm changes with time. The smoke alarm switches on when the count rate falls to 80 counts per second. So there's the counts once it's gone down to 80, which is 1.3 half-lives, the alarm is going to come on. Explain why the radiation source inside the smoke alarm should have a long half-life. So the smoke alarm switches on after 1.3 half-lives as identified by the graph. Remember, if they give you some information, make sure you use it. If the half-life is short, this means the count rate would decrease to 80 very quickly and the alarm would switch on even when no smoke was present. Alright? You don't want the count rate of the alpha to decrease. And then even when there's no smoke there, the count rate is at 80, so the alarm comes on. Usually the half-life of the alpha is a couple of years. So your smoke alarm lasts a couple of years. Sometimes it might even be 10 years. Figure 11 shows a patient who has been injected with a radioactive source for medical diagnosis. Explain the ideal properties of a radioactive source for use in medical diagnosis. Right, well, you want it to have a short half-life, so the count rate decreases quickly. You don't want to stay radioactive for ages, alright? With a short half-life, there'll be less risk to the patient. Now, the half-life, it should actually be long enough though, so that it can be made in a lab and then transported to the hospital and prepared by the medical staff before it gets injected into the patient. So a half-life of a few days should be fine. You want the radioactive source to have a low ionisation power so that less damage is done to the cells. You want it to have a high penetration power so it can easily be detected by the radiation detector. Remember, the radiation is injected inside the patient. It needs to penetrate out of the patient and go into the detector so that the detector can form a picture on the screen and see what's happening inside the body. And therefore, your radiation source should be a gamma source, and that's because it's got low ionising power and it's got high penetration. Question 7. A student investigated how the pressure exerted by a gas varied with the volume of the gas. A pump was used to compress the gas in a tube. As the volume of the gas decreases, the pressure of the gas increases. So they'll use this pump to force oil up this chamber, and that's the gas that is sealed in this part of the tube. So as the oil starts to come up, that gas in there is getting squashed. The student only recorded one set of results. Give 2 reasons why taking repeat readings could provide more accurate data. It's always the same answer. By taking repeats, you'll be able to calculate an average and you'll be able to identify any anomalies, which means any mistakes, perhaps due to human error, things like that. Part 2. Figure 13 shows the position of the student's eye when taking volume measurements. Notice the S. Explain what type of error could be caused if the student's eye was not in line with the level of the liquid in the tube. Now, that's what we call a parallax error, where things in the distance move slower than things that are close to you. And that parallax error will be due to the eye not being in the same position each time, right? Measurements, you're not just taking one measurement, you're taking measurements. So that might move up to there next time, so you need to move your eye up to there as well. Part 3. If the gas is compressed too quickly, the temperature of the gas increases. Explain how the temperature increase would affect the pressure exerted by the gas. Right, well, if there's a temperature increase, that'll cause a pressure increase, because higher temperature means the gas particles have more kinetic energy, so they move faster, and that means they'll collide more often and harder. And that is what pressure is. Pressure is caused by particles colliding. So I've put a lot of information there. It'll definitely get the 2 marks. If the same question comes up and it's worth 4 marks, there you go. You're welcome. Part 4. One of the students' results is given below. There's a pressure, there's a volume. Calculate the volume of the gas when the pressure was that. And the temperature of the gas is constant. Okay, so this is the first pressure of the gas, and that's the first volume. So when the gas is that pressure, that's its volume. What they're going to do is they're going to increase the pump to make the pressure get bigger to 1.8 times 10 to the 5 pascals. Now, if the temperature remains constant, that means that pressure 1 times by volume 1 is going to equal pressure 2 times by volume 2. And we're trying to work out volume 2. So we'll rearrange that. Volume 2 is pressure 1 times by volume 1 divided by pressure 2. Put the numbers in. The pascals as units will cancel out, and that'll just leave the volume in centimetres cubed, which was what they were wanting. So the answer is 8. I've got a video called Magic Triangle to show you how to rearrange equations if you're not very good at them. Part 5. Figure 14 shows a person using a bicycle pump to inflate a tyre. The internal energy of the air increases as the tyre is inflated. Explain why. It's always the same. When work is done on the air, remember, work done is equal to the energy transferred. So energy is going to get transferred to the air. So the temperature of the air will increase. So why has it got more internal energy? It's basically because the temperature of the air is going to increase because you've done work on it. But again, I've gave you a little bit more information there just in case it's worth more next time. Question 8. Nuclear power stations generate electricity through nuclear fission. Electricity can also be generated by burning shale gas. Shale gas is natural gas trapped in rocks. Shale gas can be extracted by a process called fracking. There is some evidence that fracking causes minor earthquakes. Burning shale gas adds carbon dioxide to the atmosphere. Describe the advantages of nuclear power compared to the use of shale gas to generate electricity. Right, I've underlined the important parts, so we'll address those straight away. Nuclear power doesn't cause earthquakes. Also, nuclear power doesn't release carbon dioxide. And off the back of that, so it won't cause global warming. Be specific and say global warming rather than just pollution. And finally, nuclear power is more concentrated than gas, which means you'll get more energy released per kilogram of the nuclear fuel. Now, I've already got 4 marks there and it's only worth 3, but I have saw an advantage of nuclear power was it'll be easier to transport. If you need less mass of it, it'll be easier to pour it in a trolley and get it somewhere. Mind, there is problems with transporting it due to the radiation. Part 2. What is the name of one fuel used in nuclear power stations? Right, it's always the same. It's either uranium or plutonium. Part 3. Describe the process of nuclear fission. Okay, so just in case this is the 6-mark question in the future, I've popped a lot of detail here. Fission. A slow-moving neutron is absorbed by a large unstable nucleus, such as uranium or plutonium, which will split into 2 smaller nuclei. Make sure you say the words large and then smaller. That'll release energy. And also, more neutrons get released. And those neutrons could create further fission reactions called a chain reaction. In some of my other videos, I've actually drew that picture. So check out those videos for the past papers. Or look in your revision guide. Question 9. Figure 15 shows a coffee machine. The coffee machine uses an electric element to heat water. The coffee machine has a metal case. Why would it be dangerous for the live wire of the electric cable to touch the metal case? Well, metal's a conductor, so the case would become live. And if someone came along, they would get an electric shock if they touched it. So that could be worth 2 marks. And that's always the same answer. And what you'd need then, because it's metal, it would need an earth wire, which is also a very common question. They might say the casing is plastic. Why does it not need an earth wire? Well, if it's plastic, it can't become live. So it's not dangerous. The earth wire, remember, would take the current away from the casing and move it to earth, and it would create a short circuit and it would blow the fuse and it would switch the component off. Make sure you know about earth wires. The power output of the coffee machine is 2.53 kilowatts. Right, remember a kilowatt is 1000 watts, so let's immediately convert that into watts. The mains potential difference is 230 volts. Calculate the current in the coffee machine. So we've got the power, we've got the voltage, we need the current, so we'll just use the equation P equals IV, PIV. Rearrange it, put the numbers in, out pops the current, 11 amps. That seems reasonable, yeah. Part 3. The coffee machine heats water from 20 degrees to 90 degrees, so that's a change of 70 degrees. The power output of the coffee machine is that, So again, I've converted into watts. The specific heat capacity of water is 4,200 joules per kilogram to make it raise its temperature by 1 degree C. Calculate the mass of water that the coffee machine can heat in 14 seconds. Right, well, remember that power is how much energy there is per second. So the total energy supplied to the water is going to be the power of the device times by how long it's left on for. So that was the power, which is how many joules there are per second. Multiply that by how many seconds you're using it for. So that's how much energy has been supplied to the water. Now the equation you need to use is the change in energy equals mass times by specific heat capacity times by temperature change. That will be given to you in an exam. So it's written like this on your insert if you're AQA. If you're Edexcel, then that equation will be at the back of the paper for you. Let's rearrange that equation to find mass. Pop the numbers in. Remember, the change in the temperature there, this delta theta, was the change in the temperature up there. And this little triangle here, that also means change in energy. And it comes out as 0.12 kilograms. Question 10. Figure 16 shows a wind turbine. At a particular wind speed, a volume of 2.3 times 10 to the 4 meters cubed of air passes the blades each second. So I've drew a picture. Calculate the mass of air passing the blades per second. So they've gave you a density, they've gave you a volume, we're looking for a mass. Is there an equation that connects those three things? Yes, there is. What is it? It's density equals mass over volume. We're looking for mass, so rearrange it to find mass equals density times by volume. There's your density, there's your volume, and that is your mass. Part 2. The power output of the turbine is directly proportional to the kinetic energy of the air passing the blades each second. So kinetic energy is a half mv squared. So describe the effect of the power output when the wind speed is halved. Okay, it's a bit trickier than you think, this one. They say that the power output is proportional to the kinetic energy, so that's proportional to half mv squared. Now, if you decrease the wind speed, so if the wind speed is halved, now the kinetic energy is actually going to decrease by a factor of 4. So it's going to be a quarter. So if you've decreased that by a half, then a half squared is a quarter. But also, if you've decreased the wind speed, you're only going to have half the amount of mass going past the turbine. So this mass here, if the wind speed is halved, the mass of the wind per second is going to be halved. So if you halve the kinetic energy and you also quarter the kinetic energy, then a half times by a quarter is an eighth. So the kinetic energy would decrease by a factor of 8. In other words, the power output will be an eighth of what it was if the wind speed gets halved. So it's a bit tricky, that one, for 3 marks. It could easily be worth more than 3 marks. Part 3. At a different wind speed, the wind turbine has a power output of 388 kilowatts. So again, 1 kilowatt's 1,000 watts. Now also 1 watt is 1 joule per second. I'll come back to that in a minute. The mass of air passing the wind turbine each second is that. Calculate the speed of the air passing the blades each second. They're going on about each second all the time. Now remember, the power output, the power is energy per second. So if they're saying it's 388 kilowatts, well remember that's 388,000 watts, but it also means it's 388,000 joules per second. Now that is very, very important. So we are trying to calculate the speed per second. So now that we know that everything is in per second, we can just pop the numbers in. So kinetic energy is a half mv squared. If I know I'm rearranging it, I'll put kinetic energy equals mv squared over 2 instead. That's the same as the half, remember. Now, I'll multiply both sides by 2. So I'll bring the 2 up here, and then I will bring the mass across down to here. Then I don't want v squared, I only want v, so I will square root both sides, and that'll get rid of the square for us, and that'll leave you with this equation. Now, they often get you to rearrange that equation, so make sure you have a good look at what I've done there. Right, now pop the numbers in, and your answer comes out as 7.49, blah, blah, blah. So I've just rounded that up to 7.5. And that's the end of the paper. So I hope that was useful. There'll be lots more papers to come as you're coming up towards your mocks and then to use in the summer exams. So if you haven't already subscribed to the channel, please like the video and subscribe to the channel. Work hard, be nice, and I'll see you in the next one. Bye for now.